we'll look into some of the previous year GATE questions based on the lecture on mobility and conductivity. So this question was asked in GATE 2010 for 1 mark. At room temperature, a possible value for mobility of electrons in the inversion layer of a silicon N-channel MOSFET is. So they're asking you the a probable value of mobility of electrons in the inversion layer. You have to see two things here: silicon and inversion layer. So in a MOSFET, inversion layer is formed in bulk of the semiconductor, and in bulk of the semiconductor, the doping will be less. So in the previous lecture we saw that as doping increases, the mobility reduces. This is doping and this is mu. As doping increases, the mobility reduces. So we are saying that inversion layer is formed in the bulk of the semiconductor where doping is less. So we expect a higher mobility in this case. The mobility of electrons, the highest value is 1350 centimeter squared per volt second. So these two options are eliminated, C and D. Between these two, B is more suitable because the doping is less. If the doping would have been higher, then this would have been more appropriate answer. That is, if you take source and drain of the MOSFET, the doping will be very high. In that case, maybe you can say that the doping, the mobility reduces, and it will be in this range, 450. So next question: the drift current in semiconductor depends on. So different parameters are given here. We know the expression for drift current. This is drift current or drift current density. Q times N times mu N times E plus Q times P times mu P times E. This we saw in the first lecture of the module. So it depends on carrier concentration and electric field. It does not depend on carrier concentration gradient. So C is the correct answer. So the current which depends on carrier concentration gradient is diffusion current. This we will see in the future lectures. So this question was asked in GATE 2011 for 1 mark. This was a linked question which was asked in GATE 2010. So each of these each of the question carries 2 marks. So yeah, there is a silicon semiconductor which is given, and the doping is known, and the other values are given. It has to calculate the magnitude of electric field at x equal to 0.5 micrometers. X equal to 0.5 micrometers. It has to calculate the value of the electric field. There is a potential applied across the semiconductor. This is 1 volt, and because of this there will be an electric field inside the semiconductor. So one thing you should know is when this doping is uniform doping. Uniform doping. When the doping is uniform, you can treat it like a resistor with uniform resistance or conductance throughout the sample. So throughout the sample there will be uniform resistance or conductance, and because of this electric field will be uniform. The electric field is uniform throughout the semiconductor bar. So we know the expression for electric field, E is equal to minus dV by dx. In this case we are saying it is uniform throughout the semiconductor bar. So they are asking you the magnitude of the field. You can write magnitude of E is equal to V by D, that is applied potential, that is 1 volt divided by the thickness of this semiconductor, which is 1 micrometer. So this will be 1 volt per micrometer, but we can see it is expressed as kilovolts per centimeter. So generally in semiconductor theory, electric field will be expressed in this unit, kilovolts per centimeter. So we can easily manipulate this This will be 1 into 10 power minus 4 centimeter, which is 10 kilovolts per centimeter. So C is the correct option. So the magnitude of electric field here will be 10 kilovolts per centimeter. It doesn't matter where you are considering the point. It could be here or it could be here. Anywhere, the electric field in this semiconductor will be uniform because of the uniform doping, and its magnitude will be 10 kilovolts per centimeter. Based on this, I'll give you an assignment question. You extend this concept and try to find out what is the drop at x equal to 0.5 micrometer. So assignment 2.4, find out the potential drop that is, or the potential difference, rather you can say it as potential difference between x equal to 0 and x equal to 0.5 micrometers. It will be interesting to solve this question, and you will get to know how the potential is varying in the semiconductor. So solve this problem. And the next part, they are asking you the magnitude of electron drift current density at this point. So we have seen drift current, it depends on concentration and electric field. They are only asking you the electron drift current, so you need not consider the whole component. So it will be Q times N times mu N times E, which is given by, we know the value of Q, it is also given in the problem, 1.6 10 power minus 19 coulombs into what is N? N is the concentration of charge carriers. So here we are doping it with donor atoms with 10 power 16 per centimeter cube. So in this case, N will be approximately equal to Nd, assuming that all donors are ionized and they are contributing for conduction. So N will be approximately equal to Nd. You can neglect the term because of the thermal generation here, because it will be much less compared to Nd. So N in this case will be 10 power 16 per centimeter cube. And mu N, it is given in this problem. Mu N is given as 1350. And electric field we calculated in the previous question, it was 10 kilovolts per centimeter, 10 into 10 power 3 volts per centimeter. So just solve this and you will get this answer. The next question, this was asked in GATE 2015 for 2 marks. It is similar to the previous question, where Nd is given as 10 power 16 per centimeter cube, and mobility is given as 1000 centimeters squared per volt second. So a potential difference is applied across this semiconductor. This is 10 volts, and hence an electric field is set up. So they are asking you to calculate the average time taken by electrons to move from one end of the bar to the other end. So what is the average time it takes to move from this end to the other end, or from one end to the other end? To calculate this time, we know the distance. We know the distance which the electron has to traverse. It is 1 centimeter. But we need to know what is the velocity with which it travels. By knowing the velocity, we can find out the time which it is taking. So what is this velocity? This velocity is nothing but the drift velocity. The drift velocity is given by mu times E. So we know the mobility of the semiconductor. Electric field is not given directly, but it is given in form of this You have to calculate from this potential difference and the thickness of the semiconductor. So take this as an assignment question and solve this. Very similar to the previous question. Find out the electric field first. Electric field you find out, V by D. Then substitute this electric field here. Then you will get V drift. And after this, you substitute the value obtained for V drift in this expression and find out what is tau, the time taken for the carriers to transit from one end to the other end, and express this tau in microseconds. Please solve this as an assignment question.